Hi. I would like to show you an example for finding the mathematical model of a resistive circuit. So this is a resistive circuit. Now the mathematical model is going to be algebraic linear equation. So it's going to be AX equal to B. So in general, A matrix is going to be a square matrix which includes independent linear equations in it. So in general, if any is the number of elements, the size of this A matrix is going to be 2ne times 2ne. So these are the unknowns, all the elements, current and voltages. If you've got any elements in your circuit, it's going to be 2ne unknowns that we have. B matrix is going to include independent source, the energy source of your circuit. So in this circuit, if it's just one energy source we've got, that is the independent power source, independent voltage source. This voltage source voltage is going to be seen here. In mathematics, these are going to be constants included there. If it is AC source, it is going to be a sinusoidal function here, of course. Now I wrote all these elements here, these 12 unknowns here, and 12. So in our example, Ne is equal to 6. 1, 2, 3, 4, 5, 6. I've got 6 elements, so 12 columns, 12 rows. So my matrix is going 12 to 12. My column matrix is going to have 12 elements in it. B also has got 12 elements in it. Sorry. Now, what is the question here is how to write this. So in order to write it, we're going to write Kirchhoff current law equations, independent ones, Kirchhoff voltage law equations, and definition relations. So I'm going to write all this now. We said we've got n elements. How many nodes do we've got? 1, 2, 3, 4. We're going to write for each node Kirchhoff current law equations. If ND is 4, one of them is the reference node, so ignore that. ND minus 1 equal 3. Node is 4. ND minus 1 is 3, so I'm going to write 3 Kirchhoff current law equations. And there are 3 meshes here. Mesh is NE is 6 minus ND 4 plus 1. So 6 minus 4 is 2 plus 1 is equal to 3. So I'm going to write 3 Kirchhoff voltage law equations, the independent ones. When you add them up, it's going to be 12 equations, 12 unknowns. Let's start from this. In order to write the Kirchhoff current law equations, I've got to determine the current references. So let me do this first. Current reference for this voltage reference is given. So the current reference for this independent source is going to be downwards according to passive sign convention. So I have chosen the other ones randomly. I choose them downwards like that. I0 is already been given. Normally this will not be given. Okay. Now write the Kirchhoff current law equation for this node. Let's start from this node and I'll make a different color for that. So this blue one. So there are 3 elements connected to this node. One of them this, so IS. Sign of IS, let me put the name as well. So this is IS. This is I1. This is I2. This is I0. So this is I0 and this is I3. And this is I4. So for this node, IS coming out of the node, so plus IS plus IS. Three of them coming out of the node, so all of them are going to be plus I1 plus I2 is equal to 0. So for this node, make it different color, maybe green. So there are three elements once again. I1 in this case, for this node, it is coming towards the node, so minus I1. This I0 coming out of the node, plus I0. And this I3 coming out of the node, plus I3 is equal to 0. And the last one, for this node, to make it black then, this one. I2 is coming towards the node, so it is going to be minus I2. I0 coming towards the node, it is going to be minus I0. This coming out of the node, plus I4 is equal to 0. So these are the independent Kirchhoff current law equations. We wrote three of these equations. Now I'm going to write Kirchhoff voltage law equations. In order to write this, I've got to choose a mesh direction. So I choose it like downwards, like that. For this one, like this. And for this one, like this. If I write the Kirchhoff voltage law equation for this for this mesh, I already know that Kirchhoff voltage law equations written for the meshes, they are independent. I'm not going to write it all loop equations, but mesh equations. So this one, same direction, so this one is going to be V1. And since the direction of the mesh and the element current is the same, it's going to be plus V1. And this is plus, same direction once again, V3, third element voltage. So direction this way and this direction is the same direction. But this direction of this mesh current is opposite to the independent voltage source current, so it's going to be minus Vs. I'm going to write that Vs on the right hand side. It's going to be easy for me to transfer it to this matrix. So that is the first one. The second mesh is this one. For the second mesh, if I write the Kirchhoff voltage law equation, so V2 is going to be plus, directions are the same, V2. This is the opposite. This current reference and this mesh reference is the opposite to each other. It's going to be minus V0. And that's going to be opposite as well. This one is going to be minus V1 is equal to 0. The last one is this one. So direction for this mesh reference and this element current reference is the same, so it's going to be plus V0. And this is the same direction, both of them, plus V4. And that is the opposite direction, I3, and this current is opposite direction each other, so minus V3 is equal to 0. So these are Kirchhoff voltage law equations, independent ones. So we've got 3, so that's the one, isn't it? Sorry, that is node equations, that is the mesh equations. So what is left is the definition relations. So definition relation of this independent voltage source is Vs is equal 80. And definition relation for the first one, first resistor, is V1 is equal to 5 I1. The second one, V2, is also 5 I2. Third one, V3 is equal 70 times I3, and V4 is 12 times I4, and this V0, so V0 is equal 10 times I0. So these are the resistors definition relations. So this is independent voltage source definition relation. Since we've got 6 elements, 2, 4, 5, 6 definition relations I wrote. Definition relations. Okay. So now I wrote these equations. So I am saying mathematical model. You can call this mathematical model as well. So I am transferring this to this format. So this is going to be my A matrix. I wrote B, of course, made a mistake. Okay, correct. A matrix. And this is B matrix. So X matrix, okay. And this is B matrix, isn't it? IX equal to B. So let's transfer the first one. Now, first one, V0, 0. IS is going to be plus 1. There is no V0, I0. V1, there is no V1, 0. I1 is plus 1. V2, V0, I2 is plus, this is plus 1. The others are 0, 0, is equal to 0. So if you write this now, multiply this column with this one, it's going to be plus IS plus I1 plus I2 equal to 0. This is this one. So similarly, so I1 is minus 1. I0 is plus 1. So the corresponding row is 9. I3 is going to be 1 plus 1. So the others are 0. I put zeros for the rest of it. So that's going to be equal to 0. So this is the second equation. Third equation, I2 is going to be I2. Where is I2? Here they are, minus 1. I0 is minus 1. And I4 is 1. This is 1. So the rest of them is going to be 0, 0, 0, 0, 0, 0, 0, 0. So this is the third equation, equal to 0. Fourth one, this time V1 here is going to be plus 1. V3 plus 1 is equal Vs. So Vs is here. If I put minus 1 here, isn't it? If I write, so I can easily do it here. Right there. Minus Vs equal to 0. So I wrote it here. The rest of them is going to be 0. So this is the fourth equation. This one, y2, where is y2? Here are 1. y0, minus 1. y1 is minus 1. 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is this one. And last one, y0 is plus 1. y0 plus 1. y4 is 1. y3 is minus 1. Rest of them 0. So this is this one. So this one, also the others are 1, 2, 3, 4, 5, 6. So that's 0. Vs, where is Vs? Vs is here, so Vs 1, rest of them 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Now I'm going to write 80 here. So it's what's going to, if you multiply with this one, Vs, rest of them 0, equal to 80. So we wrote this. Let's write this one, V0 is here, coefficient is 1. If you consider this on the left hand side, I0 coefficient is going to be 10, isn't it? I0 coefficient is minus 10, is equal to 0. So if you transfer this, so let me do it. What I have done is V0 minus 10 I0 equal to 0. This is what I have done. V0 coefficient is 1, I0 coefficient is minus 10, is equal to 0, rest of them 0. So this is this one. So this one, V2 is here. So it's going to be maybe a bit movable. So let me show it like that. V2 is plus 1. If you move this left hand side 5 high, so I1 coefficient is going to be V2. Oh, I should have write this one first, isn't it? V1 should have been. Okay. Okay. V1, where is V1? Here we are, V1. If I move this 5 I1 to the left hand side, I1 coefficient is going to be minus 5. Rest of them 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It's going to be 0, isn't it? So V2, I2, V2 is here, coefficient is 1. I2 is going to be minus 5. Rest of them 0. So I'm put it like that, zeros, 0. Two more left, so V3 is 1. I3 is going to be minus 70. Rest of them 0. And the last one, V4, is 1. I4 coefficient is going to be 12. Minus 12. And zeros here. 10 zeros. Okay. Now let's interpret our conclusion now. I have got a 12 times 12 dimension A matrix here. Since I've got any elements, 2 any is the side dimension of my matrix. In this matrix, what we are seeing, so up to here, maybe different color, up to here, not this, sorry, I should correct it, my drawing down, up to just before that. That's the one, okay. If you look at this area here, what we see, zeros, plus ones and minus ones in this. These are corresponding these equations. Kirchhoff current law equations, voltage law equations, because all the coefficients here are either 0 or plus minus 1. The others are the definition relations. In the definition relations, what we are observing here is this coefficient, you see, these coefficients. The other one is 1. You see, these coefficients are the parameters that we see in the definition relation of the elements. So in this area, let's make a green area here, which represent this area. Definition relations. In the definition relations part of A matrix, we are going to observe parameters of definition relations. What we've got here is the 2NE, which is 12. elements current and voltages. And what we've got in B matrix is this independent voltage source voltage value. So the solution of this is going to be like that, isn't it? Conclusion. You're going to find the inverse of this A matrix. Since A matrix determinant is different from 0, that means independent equations, you can find the inverse of this A matrix. So X is going to be A minus B. B is known, A is known, so you can find all the elements, current and voltages. Why we have done this, this representation, we can easily say this. Just by looking at this equation now, the solution equation, if B column matrix elements, entities, multiplied with a constant, your solution is going to be multiplied with constant, isn't it? So look at that. This, what does this mean is this A minus 1 inverse matrix is going to be a square matrix again. You're going to multiply this square matrix with B. If you look at B, you've got one non-zero coefficient here, entity. So this non-zero entity's corresponding column is going to be your solution, isn't it? So that means your solutions always is going to be V or I of an element is going to be equal something, a coefficient multiplied with source, isn't it? Vs. So you are trying to find this coefficient. So interpretation, just by looking at these equations, mathematical equations, in practical I can find out a rule. If I increase my independent voltage source voltage by a coefficient k, multiply with k, that means your solution is going to be multiplied with k, isn't it? So if I transfer it to this circuit now, if I replace this 80 volt independent voltage source with 160 volts, all my solutions that I'm going to find is going to be multiplied with 2. So you don't have to do all these to find out the inverse of a function or anything like that. That's one thing. The other thing is, if you got 2, maybe I clear this area and then show it to you. Make it a bit big. Just why I have represented all this with a mathematical model in matrix form. From this matrix form, I'm going to find 2 conclusions. Just by looking at this. Now, if I say that, let's say in this circuit, you've got 2 independent sources, not just one, like this one. So in this case, in this column, you're going to have 2 values. So you can write these 2 values like that. B1, B2. These are column matrices. Each of them represent the independent voltage source. So in this column matrix, I've got only one value, which represent one of my independent voltage source. In this one, the second independent voltage source voltage value is seen. This is another column matrix. I wrote this 2 column matrix. Summation of this is going to be my B. So if you do the multiplication, what you get, so let's interpret our solution now. Our solution, if you got 2 independent sources in your circuit, if one of the independent sources in, but the other one is deactivated, the other independent source deactivated. If it is a voltage source, the voltage made 0. You find a solution. In the second case, you're going to keep the second independent voltage source in this circuit and remove the first one by making the voltage equal to 0. So you're going to find another solution. Summation of those 2 solutions gives you my original solution. That is linearity, and practical meaning is this. There is a special name for it. It is called superposition theorem. So that means if you've got more than one independent source in your circuit, you can find your solutions for each independent source separately. Add those solutions up, gives you your original solution. That is the linearity. So this circuit is a resistive, and also all the resistive circuits are linear, of course, and this is linear because these elements are linear. So the mathematics helps you to make some conclusion of your circuit. So that's the end of this.